Hello everyone. We've been working with scatter plots and data and talking about Spearman's and Pearson's rank correlation or correlation coefficient, and today's video is going to extend that to the scatter plots and thinking about representing the scatter plots with a line, what we call a best fit line. Hopefully, before we even talk about lines, you're picturing this scatter plot and thinking in your head that this has a strong positive relationship and that maybe this even has an R value of 0.9. We don't need to know for certain, but we need to know that it's a strong positive relationship. In order to find a best fit line, we can take a line and try and draw one in. Now, best fit line is going to be the line that represents the data the best. If I draw this line too low, it underrepresents the slope of this data. If I draw it too high, then the slope might be too steep. The best fit line fits the data the best. Maybe it touches the most points, or is the closest it can be to all the possible points. So I think that looks pretty good there. Whoops. Don't want the little one. The best fit line can be estimated, but for our part, we're mostly going to be calculating the best fit line on our graphing calculator. Before we do that, I want to tell you about why we call it the least squares regression line. You may remember that in Math 1, we found the regression line, and that we just called it a regression line. It's the same process here in this correlation unit, but we call it the least squares regression line, and we're going to talk about why it's called least squares. Let's go to the next page. Here we have 3 pieces of data. Again, almost linear, a strong positive relationship here. Here are the actual data points. We could probably represent this with a line, and in fact, we're going to represent it with the line y equals x. So that's the line where it's 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. Okay, notice that maybe this isn't the best line for this data because this distance here is pretty big. This point is fairly far away from this line. Well, we can actually calculate the sum of the squared errors. We said this is the least squares regression. So we want the smallest sum of the squared errors. The way we do this is we can use this little chart. This is our actual data. If we use the equation y equals x, then our predicted y value from this equation would also be 1 with an error of 0. And if we square that, 0 squared is 0. When we plug in 2 for x, we would get a prediction of 2 for y as well. So there's no difference on that one. However, if we plugged in 3 for x, using this equation, we would predict to get 3 for y. Here, there is an error. There's a difference of 2 when we subtract those. Well, and 2 squared is 4. So when I sum my errors, my squared errors, I have a sum of 4. That's a fairly large sum of squared errors. We're going to be looking for something much smaller, and that equation that gets us a smaller sum of squared errors will be the best fit line. If we look at the next page, here we're going to try a different equation. We're going to try the equation y equals a slope of 2x minus 1.33. When we draw in this best fit line, I'm starting at negative 1.33, which is about here. I'm going up 2 and over 1, so it's going to be approximately here. Notice how that line fits those points much better, and in fact, there's not a very big difference here. And these are maybe slightly off here and slightly off here, but there's not a big long line that we're looking at. If we use this equation and plug in 1 for x, then we would anticipate getting 0.66 for y. Well, if you subtract the predicted y from the actual y, there's an error of 0.33. And 0.33 squared is 0.1089. If you plug in 2 for x, and get the y value of 2.66. Well, 2 and 2.66 have a difference of 0.66, and when we square that, we get 0.4356. When you plug in 3, you actually get 4.66. That from 5 has a difference of 0.33. Squared is another 1.089. The sum of these numbers, notice they're all decimals. When we add them, it's 0.6534. This sum is much smaller than the sum we had on the previous page of 4. So our sum of squared errors is quite small. This line, represented by this equation, is then going to be our best fit line. And we figured that out by doing least squares regression. Now this process takes a while. We might not get the right equation right away. We might have to try 2 and 3 and 4 different types of equations before we get the best fit line. It's not great to do by hand. Okay, that's why we have a calculator to help us. The calculator does this process of finding the sums of the squared errors and tests lots of different lines till it finds the smallest sum. The calculator also makes sure that the best fit line or the least squares regression line includes the centroid. Sorry about that interruption. The centroid is the point that has the mean of the x data and the mean of the y data. The centroid for this data here is 2 and 2.66, and we can see that this line includes the point 2 and 2.66. It's approximately right here. So that's another way to tell that this is a good line or good equation to represent this data. Let's try this with some actual data. And this time we're going to use the calculator because it's more efficient. If you look at this data here, we have hours of study and a student's grade on their exam. And I hope that you're thinking in your head that you're seeing a strong positive relationship here. But to confirm that, we're going to do a few things on the graphing calculator. Oops, I want this. I want you to think about doing 4 or 3, depending on what you're asked to do, specific things on the graphing calculator when you're doing the data. I want you to make a scatter plot. I want you to perform linear regression and get the y equals ax plus b equation. From this same thing, you can also get the r value, the correlation coefficient. I want you to put your line into the y equals and look at it in comparison to the scatter plot. And then generally you'll also be asked to make a prediction. And I'll show you how to do that with the line and the graphing calculator. So if we go to look at the calculator, the tech tip that you received for Pearson's correlation coefficient will enable you to do linear regression. It's the same tech tip. I have taken the data, the hours of study, and the grade on exam data, and entered it into the stat edit lists. And so the first thing we're going to do is make a scatter plot. If we adjust our window first, our data went from 0 to 6, so going from 0 to 10 by 1s makes sense, and our data went from 67 to 95, so going from 60 to 100 by 5 makes sense. Then we want to turn our scatter plot on, so I'm going to turn on plot 1, so make sure it's on the on and hit enter, and just confirm that it's on the scatter plot and then it's list 1 and list 2. So if we look at our graph, there it is. Looks like a strong positive relationship. No surprise there. To calculate the linear regression or least squares regression line, we go back to stat, over to calc. We're going to go to number 4. We're going to put in second 1, comma, second 2 to say we're in list 1 and list 2. Enter. And notice a few things here. We have A being our slope, 4.857. B is our y-intercept, 6.91. And notice our r value of 0.96. So that confirms this is a strong positive relationship. But if I take this A, 4.857 as my slope, and my B is my y-intercept, 69.1, and go back to my y equals, so I'm putting in 4.857x plus 69.1, and then hit graph, I can see that this line now is representing this data. This is very handy because if I want to make a prediction, then I can do second table and look at the data values here and say I want to know what grade I might get if I study for 7 hours. Oh, looks like I might even get over 100, 103. Linear regression lines and correlation coefficients all go hand in hand. It's about deciding if there's a relationship, if it's a positive relationship or a negative relationship, and then representing that relationship with a line, and then being able to use that line to make predictions. Good luck!